welcome to this evening's lecture organised by the Heritage Society of Engineers Ireland and this evening in association with the Geotechnical Society of Ireland. And also I welcome any other visitors here to our event this evening. I'll first of all just draw your attention to the exits from the hall in the unlikely event of fire or other emergency. They're the way you entered and through the emergency doors in the right-hand corner of the hall. Now, our joint presenters this evening are both chartered engineers, Trevor Orr and Fintan Buggy. Now, Dr. Orr is an associate professor of civil engineering at Trinity College, and Fintan is an associate with Roughan O'Donovan. Both those organisations are obviously well known to you. Both have many years' experience in the field of geotechnical engineering, and their presentation will focus on the civil engineering achievements of a 19th century County Surveyor of Louth, John Neville. His dates coming in said 1913 to 1989, but I think he was a little bit earlier than that, the previous century. Anyway, in particular, he did many things, but in particular, he tried to present the state of knowledge at the time concerning earth pressures. And hopefully in the joint presentation, we'll see some indication of how the theories have changed over time, but starting with John Neville. So it gives me great pleasure to invite Trevor and Fintan to present their lecture, which they have entitled John Neville, 1813 to 1889, and Fintan is to go first. Fintan.
Thank you, Ron. First of all, I'm sure most of you in the audience have probably never heard of John Neville, and certainly I had never heard of John Neville until Ron Cox brought him to my attention a couple of years ago now. At the time, the Geotechnical Society was looking for some interesting historical characters that we might use to give a named lecture for. And Ron suggested that John Neville was a suitable candidate, and he was proposed, but in the end the Society selected another engineer to name for its lecture. But anyway, that's in the process of looking at the history of John Neville, I was intrigued about his history. And you might note that there is another historical engineer called Parkes Neville. Parkes Neville was a president of the institution in the 1880s. There is no relationship between the two Nevilles. This John Neville was completely separate character and not related to Parkes Neville. So just to give you an outline, I'll talk a little bit about his professional history and family, a little bit about the role of county surveyors in Ireland, what John Neville was involved in terms of roads and bridges in his county Louth, his interaction with railways and other public works that he was responsible for, private architecture practice, that's not a big focus of today, but he was active in that area, and a little bit about his publications. And then I will hand over to Trevor, who will go through the publication and some of his works in relation to earth pressure theory. And we'll sum up and give some acknowledgements at the end. So briefly, John Neville was born in Limerick in 1813. We don't know much about his initial education and training, although we know that his father, also John, was an architect. He worked on the Shannon navigation in Athlone in his early years, detailed river surveys and locks between Athlone and Meelick. He also got some experience as a road contractor between 1838 and 1840 in his 20s. He was appointed as a Louth County Surveyor in 1840, and he resigned in 1886 due to ill health. So he was 46 years tenured as the County Surveyor, one of the longest serving County Surveyors ever in Ireland. He was also had a number of other titles, Borough Surveyor in Drogheda and Dundalk, Engineer-in-Chief of the Dundalk Harbour Commissioners. He was a member of the Royal Irish Academy, the Royal Geological Society of Ireland. He was a member of this institution. He was both a council member and a vice president of this institution, the Institute of Engineers of Ireland, in 1864. He was also a member of the Masonic Order. Personal background, Neville was a Catholic, and obviously in the absence of emancipation in the 1829, he would never have been able to take on such a public role as he did in public office. So he was a product of his time in terms of how Catholic emancipation opened the doors to these types of professions in Ireland. He interestingly married a Protestant lady in 1849, and the family lived in a number of residences in Dundalk, and they also owned quite a bit of property in County Tipperary. They had 2 daughters. Both became nuns in the Sisters of Mercy. They had 3 sons, all raised as Protestants, the most significant of which, William, was a gynecologist and lived in Dublin. He had another son, an engineer. Neville died in June in 1889 at his eldest son's residence in Baggot Street in Dublin. So who were the county surveyors? How do they come to be? In the early 19th century, local responsibility for public works rested with the grand juries. These were up to 23 appointed members of landed gentry, and there was 1 per baronry, typically. Grand juries voted on proposals every twice a year before the law courts met. Their decisions were confirmed by a judge, and payments for the costs of public works were made on completion from the local taxpayers. The system was highly prone to corruption, fraud, inefficiency, and waste. A lot of things went on. Proposals were made for personal gain, not for public interest. Sometimes payments were made directly to landowners in lieu of rent from tenants. Typically, the grand jurors had no engineering construction expertise. You can see how a system was prone to a lot of problems. Reform was first pursued in the early 1800s. In 1817, the Westminster Parliament passed a law to appoint surveyors following examination and certification. But and regrettably, out of 95 applicants in 1817, forgive me, the date is wrong there, should be 1817, only 3 were deemed competent and none were certified. So the reform was held in abeyance for some years until it was revised again in 1833. And in 1834, finally, 32 county surveyors were appointed. None were formally trained in engineering. There were no such courses available for civil engineers in Irish and British universities until later in the 1840s. Neville was appointed in 1840 with a salary of £400 per annum. He took and failed initially the exam in 1838, but he gained some further experience as a road contractor, and that qualified him to be a county surveyor. He was an agitator and campaigned for modifications to the grand jury law to allow consolidation of road maintenance contracts. The situation he found was that there were a huge number of contracts for relatively small amounts. He wanted to condense these into far fewer contracts, arguing that this would reduce admin costs, get better quality of contractors involved, and get a permanent experienced workforce involved in doing road construction and road maintenance. He was voted on that case, and his proposals were not adopted. He also campaigned to have more assistant surveyors with higher qualifications and salaries. He had personally 4 assistants, but had to actually pay additional monies to their salary beyond what was available from the public purse. And he decried on one instance that regrettably one of his assistants died falling off his horse, and he'd have to pay him another assistant now. In 1846, he published a paper setting out legal and organizational defects in the county surveyor system, and this was published by Dublin University. It was initially refused by this institution for publication. So Neville was an agitator for change, and he took on vested interests, and his message was not always welcome. He resigned, as I said, due to ill health after 46 years in office. In terms of roads, he supervised a county system, started with about 400 miles in County Louth in the 1840, and this had increased to nearly 600 miles 25 years later. There was no direct labour. All of this work was done by contractors. During the famine years, however, the system was enlarged hugely to take on direct labour because of the social consequences of famine. And at one stage, he employed over 6,000 people on famine relief schemes. He actually wanted to retain direct labour as a system to maintain and build roads, but was quite unsympathetic to the social purpose of employing women, children, and the infirm for that purpose. He argued to abolish turnpike roads, and these had high staff costs and usually insufficient money left over for maintenance. And in the 1850s, responsibility for all the turnpike roads left in Ireland reverted to the grand juries and the individual county surveyors. So he was successful in that area. Now, the Irish road system was the subject of a quite interesting goods and passenger traffic survey in 1838. This was by the Irish Railway Commission, but it gives a sense of what the status of Irish road traffic was like in the 1830s when Neville first took up his post. Now, these two maps show the variation in goods traffic. The map on the left shows goods traffic, and the thickness of the line shows the volume and tonnage of goods being transported around the country. And you can see primarily goods traffic was coming in and out of the country from the main ports: Dublin, Belfast, Waterford, Cork, and Limerick, and then some minor ports such as Drogheda and Dundalk and others. And the primary traffic was radiating from those sources of import and export of goods. Plus, there was significant traffic along the two main canal systems, the Royal and Grand Canals connecting to the Shannon, and also the Barrow Canal and river system connecting down towards Waterford. On the right-hand side, the map shows passenger traffic, broadly similar but slightly different in some respects. You'll note that there was a significant amount of passenger traffic on the corridor between Belfast and Dublin. And of course, that would have passed directly through County Louth, and Neville would have been responsible for the primary passenger traffic route through his county connecting Dublin and Belfast. This is the traffic of the day. The upper graphic shows goods wagons, horse-drawn, of course, and the lower one, a Bianconi passenger wagon with a lot of people outside and a few comfortable people on the inside who probably obviously paid the premium for travel. Traffic was extremely slow in those days. Typical average speeds of about 8 miles an hour. It would take you 12 hours and a full day, if you're lucky, to get from Dublin to Belfast on a passenger traffic by road. It would take you more than a day to get from Dublin to Cork by road, and frankly, probably quicker for you to travel by ship between Dublin and Cork than it was to go overland. Neville published some papers on road construction and how to maintain roads in 1846. He suggested that although currently a lot of roads were laid out with crossfalls of 1 in 24, that's about a 4% fall, he was arguing for crossfalls on the order of 1 in 48, about 2%. And any road engineers here would know that 2% is a common crossfall applied to current roads. So not much has changed in the 150 odd years since Neville proposed typical cross sections for roads. Neville had a mixed history as a bridge engineer. An early bridge was constructed that was reported to be poorly built, but only replaced actually quite recently in the 1980s. In St. Mary's Bridge in Drogheda, he originally had a design for a 60-foot arch design. quite a decent span for its day. This was later revised to a 2-span masonry arch structure and was only actually replaced in 1980s. There were a lot of delays due to the first contractor defaulting. The second contractor ended up in legal dispute with Neville, and arbitration found in the contractor's favour. Tender cost of that bridge was nearly £7,000 in its day. St Dominic's Bridge was another bridge, rather crude bridge, timber bridge, replaced later in the 1890s by a steel structure, and that structure is still used by pedestrians to this date. He unsuccessfully competed for the new Carlisle Bridge in Dublin, built in the 1860s, and that's now O'Connell Street. Here's a picture of the St Mary's Bridge in Drogheda. This is quite an old photograph. You can just see the spar of a ship on the left-hand side of the photograph. Gives you an idea of the age of the photograph, probably in the late 19th century. That bridge, unfortunately, no longer exists. The one bridge which does still exist and bears a loss to Neville is the Obelisk Bridge over the River Boyne. This replaced a wooden structure at Old Bridge, near the site of the 1690 Battle of the Boyne, and this is quite an achievement in terms of the span and arrangement that was constructed in this day. It was named after an obelisk which memorialized the crossing point of King William. The obelisk, unfortunately, was blown up in the 1920s. This was a single span, 120 foot, 11 foot deep wrought iron lattice girder structure, designed by Neville, although it actually crossed between two counties, between Louth and Meath, but Neville was the only engineer actually acknowledged on the plaque on the bridge, and so he is deemed to be the primary designer. Built by a local contractor, cost of £2,500. There's a very detailed description and explanation given by William Stripe in Transactions of the Civil Engineers of Ireland later, and if anybody has any interest in how exactly a lattice wrought iron Victorian bridge was constructed, you could do no worse than just read this. It's about a 18-page blow-by-blow, bolt-by-bolt account of exactly how it was built. The southern abutment was reused from the earlier structure, but the northern abutment was founded on gravel subsoils. And interestingly, the main girders were manufactured in Drogheda. They were transported on a barge 4 miles upriver on pontoons. They were set onto temporary supports, and the River Boyne was tidal at that location, and so as the tide raised and lowered, they managed to incrementally jack up the system and raise it on temporary floating supports, lifting the bridge beams at each high tide, and that's how the bridge beams were lifted into their final location. This is a picture which predates when 1920s, when the obelisk was blown up. So there stands the obelisk and Neville's Bridge. Here's a later photograph. The photographs I'm thankful to Ron Cox for providing. And here's a more current photograph of the bridge, which is still used today. I believe it has a 5-ton weight limit. Obviously, only takes single file traffic, but still a good-looking bridge and a significant achievement of a single span of that size. Neville, like many other county surveyors, were, unlike some county surveyors, was not involved in the planning and construction of railways. Neville considered this as a direct conflict of interest. He actually took legal action against railways on a couple of occasions to enforce reconstruction of railway bridges on the Dublin and Belfast Junction Railway in the 1840s. So John McNeill was the chief engineer, and very interestingly, at that time, McNeill employed a young assistant working on the railways in Ireland, and his name was W.J. McCorn Rankin. And Mr. Rankin will appear later in the presentation. Neville also opposed extension of railways into the quays at Dundalk, again arguing against the restriction of public access. He didn't have a lot of luck with railways because in 1853 he was injured in quite a serious train crash near Strafford when the Cork-Dublin Express broke down and a goods train ran into the back of the train, passenger train that Neville was in. There were 16 fatalities and nearly everybody in Neville's carriage was killed. He was extremely lucky to survive with a broken leg and some other injuries. Other public works he was involved in included dredging, draining walls, a graving dock for Dundalk Harbour. Not all the works were finally completed to his designs, however. He did a county courthouse extension. He was responsible for the architectural design and construction of the Louth County Jail in Dundalk, and that was later converted and is still used today as a Garda station. He did a small bridewell in RD. And this is a picture some years ago now, but still the structure still stands. It is the Garda station in Dundalk to this day. Fine looking structure. Private architecture. A number of county surveyors were involved in private architecture, and Neville was quite significant amongst these. Surveyors could not work for other contractors who were involved in public works, but they could accept commissions from other persons, and so private individuals who wanted to hire county surveyors as architects were free to do so. He designed a number of shops and stores in Dundalk, including what was originally Martin's Wine Stores. This is a graphic of it, and this building stands to this day. He designed a number of private homes in County Louth, Shanless House, RD House, Shanless House in RD, Dowdstown House and Carterstown House in the 1860s. He also designed, as architect, 5 chapels and convents for the Sisters of Mercy in various counties, and of course, you recall that both his daughters were members of that religious community. And this is a graphic of one of the convents of Mercy in RD. He made a number of contributions to civil engineering education through his publications, and when Neville was appointed, engineering schools were just beginning to be formed. Engineering chair in Glasgow in 1840, Trinity College Dublin in 1842. So civil engineering education was just getting going, and of course Neville came in slightly before there was a formal education. So it caught the next generation after Neville, but not Neville himself. Many of those involved in civil engineering design basically read books, read papers, Encyclopedia Britannica. These were standard sources of information for its day. And Neville, as I said, made a number of contributions through publications. He wrote a short paper on water pressures on cofferdams. The paper that Trevor will talk about in far greater detail in the first transactions of this institution on earth pressure. Road cross sections, I gave a graphic of which earlier in the presentation. And quite a successful publication he did, which was reprinted twice in London on hydraulic tables, coefficients and formulae for discharge of water, published in London, and another hydrodynamics pamphlet in the 1850s. So his interests were quite broad, well, by no means just in the area of roads, but also hydraulics. I just like to acknowledge Christine Casey, who is a lady who wrote a very interesting paper, mostly focusing on Neville's architectural achievements, which I have not really touched on in any detail today. But she wrote an excellent paper about Neville, and she writes the following about him as an individual. A cold and unemotional man, confident and assured by nature, no time for false modesty or even at times diplomacy, single-minded to the point of ruthlessness in the pursuit of quality and efficiency. And that type of individual qualities come through in the actions, the people that Neville took on, vested interests, the professionals throughout his history. In 1844, as I mentioned, the death of his assistant county surveyor, he was shockingly brief and to the point when he reported this to his superiors at the assizes. I regret this assistant has been killed from a fall from a horse a few days since, that I will now have to provide another. The report to the county roads has been printed, etc., etc. So not a lot of empathy for his dead assistant, I'm afraid. So that's a little bit about Neville the man. And now I'll pass on to Trevor, who's going to talk about Neville's impact on earth pressures.
Yes, well, I'm going to look at his contributions in the area of earth pressures as a sort of geotechnical engineer. He published this report that we mentioned earlier, Communication, in Volume 1 of the Transactions of the Institution of Civil Engineers of Ireland in 1845, and it was called An Investigation of Some Formulae for Finding the Maximum Amount of Resistance Behind Banks of Earth or Other Materials, and the position of the fracture requiring that resistance. And was read to the institution on May the 13th, 1845. I'm not sure if it was a Friday, but anyway, that's when he read it. Now, the design situation that he was involved in, he was involved a lot in cuttings and embankments, and he wanted to cut the toes of slopes using small retaining walls, for which the technical term at that time is called dwarf walls. So you have your cutting there, and the dwarf wall is the little wall to give you a bit more, reduce the amount of earth and increase the cutting. So the advantages of dwarf walls, they act as fences, the land required is reduced, there's less earthwork, and the toes of the slopes are neatly defined, protected and permanent. And that in those days was important in districts where cattle or swine abounded, according to his paper. This is in his paper. Now, the requirements to determine the dimensions of walls. To determine the dimensions of the dwarf walls, John Neville needed the earth pressure R there acting on the wall. And this depends on the slope of the ground surface proceeding from the top of the wall. So there's that, the angle theta up there. The angle of repose, which is our phi dash value. The gravity of the stuff, W, in other words, our gamma value. And he didn't refer to soil or fill separately, but treated them both as the same. And the other parameter he needed was the height of the wall, and then the height of the slope within certain limits. So there was the overall height and the height of the wall there. But you see, the problem was he didn't show any of his parameters on his figures. You have a lot of labels, but no parameters shown. Now, the objective of the analysis, let's say, was to determine the maximum horizontal resistance required to stabilize the slope. And he examined the stability of a prism, BFCD. So BFCD was the prism he was trying to analyze. So basically he had two triangles, that one there minus that one there. And he was analyzing the stability of that, sliding along the failure plane, going up from there, C to F. So that was his failure plane. And the slope of the failure plane is phi. And it's not obviously our friction angle. We now call that our friction angle. So he was using the same symbol for something different in those days, which again causes a bit confusion when you're trying to read it nowadays. So note, Neville's phi is not the same as our angle of friction, which I've called in the rest of this presentation phi dashed to avoid the confusion. Now, the trapezoidal analysis. He assumed in his analysis that there was friction on that slope and also behind the wall. And he had an angle of friction, F, or coefficient of friction, F. That's what that F is there and the F there. So we then resolve those forces parallel to that plane there to get equilibrium in that direction. And he got that equation. So you got the two components of that, and that force there and that force there, giving equilibrium equation. And resolving it to get equation for R, which is trying to calculate, you get this equation, G 1 minus F tan phi over F plus tan phi. Now, since he needed the maximum earth pressure, he differentiated that R with respect to his phi angle, his inclination of the failure plane there, phi, and he gets this equation. Tan squared phi plus 2 tan phi is equal to Fm plus m over F minus 1. Now, the equation m is h minus h squared over h minus h over h all squared times tan theta. So m is a function of theta, and if you're going to be differentiating this, it gets geometrically it gets quite complicated. And but solving the quadratic equation here, he gets this equation here for tan phi. Again, he was a great one for trigonometric functions. Sec theta tan b times square root of tan b tan c plus 1 minus 1 over tan c. And he made a substitution here. Tan b is equal to m, which is like what we had up here before. So tan b is equal to m. That's h minus h squared, h minus h over h all squared tan theta. And c then is the complement of the angle of repose. So that c up here is 1 over f, 1 over tan phi. And if the ground happens to be horizontal behind the wall, so we bring our h up to the full height, then h is equal to h, and tan b then becomes 0, because you got tan theta of 0, so that becomes 0. And the equation for tan phi, which you're trying to find, reduces to this. So we get tan phi is equal to sec minus 1 over tan c. Now, he's a great man for his trigonometric identities as well. So he knew that that gave him tan 1/2 c, which is the complement of the angle of friction. And tan phi then, if tan phi is equal to tan 1/2 c, then phi is equal to 1/2 c. And he says that his paper is that it's the equation of Prony. And it's the inclination of the plane, CF, giving the maximum value of the angle of earth pressure. So how does that then compare to what we have today? Or who was Prony? Well, first of all, let's look at Prony. Who was he and what was his equation? Prony, Gaspard de Prony, born in 1755 and died in 1839. So a lot of things were happening in engineering around this time, the end of the 1700s, beginning of the 1800s. He was one of the founders of the École Polytechnique. He was the first professor of mechanics in that school, and in 1798, he became the director of the École des Ponts et Chaussées. And his 2 books on hydraulics and 1 on mechanics were widely used in French engineering schools. So the engineers who set up engineering schools, and their equations obviously were known outside of France. Maybe they not only spread the revolution, they also spread engineering throughout the world, it seems. And then in an elementary course in civil engineering by this M. Scanzin, he states, Prony demonstrated in his Mécanique and formerly in his memoir, printed in 1802, for use of students, that the position of the differential prism at the maximum pressure is such that the inferior surface makes with a vertical line an acute angle, which is equal to half the angle the Earth naturally takes. Now that confused me a bit at the time, because makes with the vertical and acute angle. So he's talking about this angle up here, the phi angle here. It's equal to half the angle the Earth naturally takes. Well, the Earth naturally takes an angle of, we would say, phi, slope. But what he meant, angle to the vertical. So he meant the half c there. So he's referring to the angle, and that's Prony's equation. phi is equal to half c. So he's really talking about a half the angle with the vertical there. Now, if we take this angle, how does it work out with the orientation of the friction plane? Phi is equal to half c. So expressed in our commonly used symbols today, with alpha for the inclination of the slope from the horizontal and phi for the angle of friction, that gives us 90 minus theta, or 90 minus alpha, is a half of 90 minus phi, and that's equal to 45 minus phi over 2. If you rearrange that, you get alpha is equal to 45 plus phi dash by 2. And that's the expression used today you expect to get for your failure of your failure surface, 45 plus phi dash by 2. If you did a triaxial test, you'd expect to get the slope failure at that angle. So this is the angle normally used today for the effective angle, the active angle of failure. Now Coulomb in 1776 was a French physicist. He's probably better known for his electricity, Coulomb's law, and other areas, but also was involved in geotechnics. In 1764, he was sent to Martinique in the West Indies, and he was there put in charge of building a new Fort Bourbon. And he published his paper, Essai sur une application des règles de maxime et minime à quelques problèmes de statique relative à l'architecture. I think there should be a few accents in that. I copied it without, and the one I copied it from with no accents on it, but we'll leave it. And this is the first study of the problem of lateral earth pressure on retaining walls published anywhere that used the limit equilibrium theory, considering the failing soil block as a free body to determine the limiting horizontal earth pressure. In other words, to use a wedge analysis, which Neville used not so long after that. But he, in his analysis, he ignored, in fact, the friction between the soil and the wall. Also, his paper was not very readable. He used lengths rather than angles. So it was very intractable. And Prony, who took up his work, simplified it in 1802 and presented it in the now familiar trigonometric form. But Coulomb was left a legacy as a pioneer in the field of geotechnical engineering excuse me, for his contribution to retaining wall design. And his name is one of the 72 names that's inscribed on the Eiffel Tower. Now, if we move on and then look at Neville's earth pressure. So having got the critical angle, the phi dashed, for h equals h and the phi value to give the maximum R value, Neville's equation then becomes R is equal to that, h squared w over 2, sec squared minus 1 over tan c all squared, and that becomes h squared w over 2, tan squared a half c. And since half c is equal to 45 minus 5 dashed by 2, this gives the equation then that we're familiar with for the active earth pressure, which is that the R is equal to a half gamma h squared, tan squared 45 minus phi dash by 2, or gamma h squared over 2, 1 minus sine phi over 1 plus sine phi, which is the normal Ka, the equation for Ka, coefficient of earth pressure, which is still used today. Now Rankin, who was mentioned earlier by Fintan, excuse me, Rankin produced his earth pressure theory in 1857. That was after Coulomb and after Neville produced his one. And he published his earth pressure theory in this volume on the stability of loose earth in the Transactions of the Royal Society of London. And the general principles are set out there. And basically what he was looking at, if you look at the principle at the bottom there, he was treating the resistance to displacement by sliding along a given plane in a loose granular mass is equal to the normal pressure exerted between the parts of the mass on either side of that plane multiplied by a specific constant. So he wasn't looking at wedge analysis. He was looking at planes of failure, homogeneous planes of failure through the system like that. Planes of limiting stress. And Rankin's equation then for the active earth pressure is that R is equal to gamma h squared over 2, 1 minus sine phi, or 1 plus sine phi. Now that's what Neville got earlier. So I wonder when Rankin was in Dundalk and maybe met Neville, was there any communication between them? And was there any link between those two equations? Unfortunately, I don't think we can ever prove it, but it is interesting to think that maybe Neville did contribute to what Rankin eventually published only a few years later. Now, the angles of repose. Neville says that most materials in a loose, dry state have angles of repose. In other words, angle of friction phi dash between 34 and 40 degrees. A material stands on slopes between 1.25 to 1 and 1.5 to 1. In other words, nearly 33.7 degrees to 38.7 degrees. However, if the stuff or plane of fracture, in other words, CF, becomes saturated with water, the friction on the plane is reduced thereby, and the angle of repose becomes flatter. He notes that it appears that through the agency of water reducing the friction, the resistance required is double that required when the stuff is dry. So that was he was writing in his paper in 1844, that the angle of friction was reduced by half. And this is totally consistent with what we now understand through effective stress analysis, that the safe angle of an infinite slope is reduced by 1/2 when the water, or approximately 1/2, when the water rises to the surface. And design engineers would take that into account. So hence, he states the necessary of cutting or draining off water from the back of banks, slopes, and retaining walls. And certainly all engineers today, geotechnical engineers, would be very cognizant of that and very careful to do that. So he certainly was ahead of his times, and certainly was a very, he had good engineering judgment, good knowledge. Now he refers in his paper to the Rosberg great fall. So I went to the internet to find exactly what that was. He said it was an example of that proved his theory. And Neville said springs are the most general cause of landslips, and as an example refers to the great fall of the Rosberg in Austria in 1806. So that's a map of Austria, or a map of the part of Austria where the Rosberg failure occurred. It was at this place called Galdau, or Galdau, 1806 landslide event. And this map and the report was from a paper published not so long ago, 2010, by Thorough and Hallam in the Geologically Active, a volume edited by Williams et al. And in that they say that the Swiss physician, Dr. Carl Zeh, who witnessed the landslide of Galdau, said September the 22nd, 1806, the Swiss village was destroyed by a landslide with an estimated volume of 40 million cubic meters coming from the Rosberg, and 457 people were killed, and was one of the greatest natural disasters in the Alps in historic times. And then going back to Neville, he quotes Phillips' geology, saying this was a case of a kind of where water entered and moistened a particular layer of strata, all inclined very highly, so as to acquire a descending force, and if the cohesion of the part were weakened by the interposed moisture. He then states, water lubricates fissures. Now I think most people would be horrified to see that these days, but maybe in his day that's acceptable. Water lubricates fissures, decreases friction, that's certainly true, and increases the value of R. So that was an interesting situation there. That's a picture of the Rosberg Great Fall itself. And you see there have been several falls on that case. And the one that was his one, there's the prehistoric slide. The 1806 one is number 3. And it's that brown one up there. That's the one that occurred in 1806. And then the poor town I think the buried is down there, Goldell. Now, Neville and Treadgold. Thomas Treadgold was a highly respected pioneering civil engineer and the person who gave the influential definition of civil engineering on which the Charter of the Institution of Civil Engineers based itself in 1828, and includes the phrase civil engineering is the art of directing the great sources of power in nature for the use and convenience of man. So obviously Treadgold was a very eminent, respected man in his time, but as Fintan has said, Neville was not averse to criticising his peers. And in 1843, Treadgold published a table of retaining wall dimensions in the 7th edition of the Encyclopaedia Britannica. In other words, 2 years before Neville published his paper. And Neville was very critical of these tables. He wrote in his paper, they must appear to a practical person as worse than useless. And if they had been shown that the dimensions for retaining walls, and it has been shown that the dimensions for retaining walls have been calculated for an amount of resistance only half what it should be. So he felt he had to obviously write something and put things to order. So he published it, and in his paper to the Royal Irish Academy, which is subsequent to the one actually to the institution here, he identifies the error, which is that the term tan C plus 1 over tan I in Treadgold's equation for R should have been tan C tan I plus 1 over tan squared I, where C is the inclination of the back of the wall and I is the complement of the angle of repose. So he wasn't afraid to take on the most eminent people in his profession at the time. And if you take an example, say when C is 0 and I is equal to 90, or I is equal to 90 minus 30, giving 60, then if you use Treadgold's equation, you get 0.58 in his equation, whereas if you use the correct one that Neville gets, it's 0.33, and that's where the difference of about a half occurs in the calculations. It's more complicated than that because there are various factors involved in the calculation, other factors. So Neville's conclusions on earth pressure. He says that R is the most important element involved in the equations for determining the dimensions of retaining walls. Groundwater is the dominant cause of slips and cuttings. Non-planar failure surfaces are often observed in practice. When stuff is tipped into an embankment, the angle of repose is least, and when adhesion and consolidation take place, it is greatest. He noted the dangers of surcharge loading to the stability of key walls and cut slopes. Failure may not take place immediately after a fracture to the bank takes place, but after it is penetrated by water, when the angle of repose is reduced, and perhaps also hydraulic pressure is brought into play. Hence the necessity of taking the maximum value of R and the prudence of the engineering maxim stronger than strong enough. So he obviously always believed in having a factor of safety up there, is stronger than just strong enough. All these demonstrate an impressive insight into the real behavior of soils and could be made by any geotechnical engineer probably working today. So summarizing him as an engineer, he was a very distinguished engineer and one of the longest serving county surveyors. He was involved in design and construction of many public works, including roads, bridges, and public buildings. He operated a successful architectural practice. He had very good understanding of engineering principles. He was aware of recent engineering theories from Paris and was aware of what was happening in Europe, for example, in Austria. And his mathematical and analytical skills were very good, and he contributed to the early civil engineering education and continuing professional development through his publications. So that is really all I want to say. I just want to then put a few acknowledgements there. Ron Cox, who instigated the research in 2002 and provided photographs of the Obelisk Bridge. Engineers Ireland, the Royal Irish Academy, and the Institution of Civil Engineers, who all provided copies of historical papers from the libraries. John Neville, County Louth Surveyor, from Christine Casey, in the Journal of the County Louth Archaeological and Historical Society. and Irish County Surveyors 1834 to 44 by Brendan O'Donoghue. Thank you.
Well, thank you, Trevor and Fintan, very much. I thought that before I came here that the title was a little bit dry, but in fact it's been very interesting. Not only the person, but also the theories as well. I just about followed all the phi's and the phi dashes, and I think that his contribution to engineering knowledge certainly up to now has not been acknowledged. So I think both authors have put that right. But a couple of observations en route. One was the picture of the Obelisk Bridge, the present picture of the Obelisk Bridge, which in fact it was my colleague Dermot O'Dwyer took it, not me, but I'll take the credit for it. But there was two men in a rubber boat underneath the bridge. I don't know whether you noticed that. And it was actually a visit by the excuse me, a visit by the Industrial Heritage Association of Ireland to the Boyne Valley sites, and we were one of the structures we were to look at was the bridge, and we decided we reached the bridge just about at lunchtime, and we'd take our sandwiches and have a nice picnic by the side of the river and so on and so forth. Unbeknownst to us, excuse me, unbeknownst to us, there had been a security alert, and that somebody was going to come down from the north of Ireland and blow up the Obelisk Bridge, hence the rubber dinghy underneath with the men in it checking to see whether there were any explosives underneath the bridge. And all along the banks there were armed police and armed soldiers equally having their lunch. So we went up and said, can we have our lunch here too? And they sort of looked at us. But anyway, that's why there were people in the rubber boat underneath the bridge. The other thing I noted was that from the point of view of exchange of knowledge, the transactions of the institution would have been quite widely distributed, because in those days, well, I say the 19th century anyway, certainly, when the institution was very active with its proceedings and so on, the library, which is sadly now gone, used to take copies of all sorts of journals and books from around Europe and further afield in exchange for their own transactions. So those transactions would have been certainly known to people like Rankin and so on, who hopefully would have read it before he did his research, maybe 10 or more years later. Anyway, are there any other comments now from the audience? Come on.
Yeah, thanks very much for the presentation. What possessed him to do all this work on earth pressures? What was the problem he was solving? Was there one major thing that he was working on, or?
Authors, I suggest you stand here so that you can be seen online. Other two.
Well, I think it was in the context of building these dwarf walls. So I think he was involved in obviously mainly roads, I think, roads, cuttings and embankments for roads. And he wanted to reduce the amount of land take and amount of fill. So he's building these dwarf walls and wanted to know the pressure on them so they'd be stable. To calculate them, he wanted a method for calculating the earth pressures on those walls.
So it's a road building primarily.
Yes, a road building background.
Yes. I mean, I'm sure he was probably under pressure to minimize land take from private landowners. So the idea of dwarf walls was driven by that. And I think you can see from his comments that he was knowledgeable of failures. This was a practical engineer who was a builder and had seen failures and had understood or had learned from failures. And so I think that was a driver within his own sort of professional recognition, that he had experienced successes and failures, and he was driven to better understand why certain applications of walls were successful and others had failed. So that would be my sort of view, reading a little bit between the lines between what he wrote.
And he certainly, in his conclusions, reports what he found, like the water pressure causing failure to occur more at lower pressures, and the curved failure surfaces, things like that. So he refers to those things from his observations.
Thanks, that was very interesting. The one thing that strikes sort of things in my mind is there was a presentation a few years ago on rampart roads and peatlands across Ireland. Not the same type of footprint where the road is built up and kind of carved out from a soft area. Is there any suggestion that he had looked at that type of work previously, or that was influenced by that, or do you have anything to suggest?
I don't know. I don't think there's any direct connection between rampart roads in peat lands, which is what I think what you're referring to, and what Neville was referring. You know, his word for soil and fill is the stuff. Very interesting. So he doesn't discriminate between different soils, but I think you can kind of tell from his description of the typical angles of repose of the stuff between 34 and 40 degrees that he probably wasn't looking at trying to make these walls stand up in peat cuttings, because you know, no peat is likely to be that strong a material you know, over a long period of time. So I'm guessing that he wasn't probably involved in looking at peat stability as much as the more typical soils that he would have found in County Louth.
County Surveyor,
Yes, indeed. Yeah.
It was 2,200 miles of roads, wasn't it, increased by in County Louth during his time. So it was probably mostly those roads he was concerned with.
Well, one thing comment I'd like to make is I think we have an idea in engineering that another character comes along, all of a sudden a new theory is made and science makes this dramatic jump and we move on. So we've had Coulomb. Coulomb is probably one of the best known names in geotechnics for many years. And then nothing happens, and then all of a sudden we hear of Rankin. Rankin is by far much more well known in geotechnics than Neville. No one's ever heard of Neville. Rankin, in actual fact, is a scientist, not particularly a scientist in engineering, but Rankin is far, far better known for his work on heat engines. This is really what Rankin was a scientist about. He did a lot of research in Scotland on heat engines and the subject of what we now call thermodynamics. Rankin only wrote one single paper on earth pressure and in his entire professional career. And for that one paper, he is by far a very well-known engineer, and in fact, a very prestigious prize is given by the Institution of Civil Engineers in London, the Rankin Lecture, given every year in London. And then we move on, and in the 1920s and 30s, another character comes along called Carl Terzaghi. Carl is considered the father of soil mechanics because of his insightful idea of effective earth pressure. And this was the beginning, really, of the modern science of soil mechanics that most geotechnical engineers would consider. And he published that in the 1920s. But I think that the reality is actually a lot more nuanced than that. And Neville is an example of another practical engineer striving and working in his day. And in actual fact, he made a big progression from what he knew from Coulomb and Prony to where subsequently Rankin and others who took on the idea of geotechnics in Terzaghi. So he was a sort of an intermediate character, but I think you can tell that yes, he didn't recognize what effective earth pressure meant, but he really understood what the influence of groundwater would have on a practical geotechnical problem. So, you know, he didn't quite have the understanding of a modern geotechnical engineer, but he was clearly moving in that direction, and he made a lot of references to the significance of water pressure. And perhaps if he wasn't such a practical engineer, perhaps if he was employed in a university and had the opportunity to do more research, he might have grasped the ideas that later Terzaghi did. But you know, that wasn't within his ability for the man that he was of his times. But he's an important character nonetheless, and deserves just as much credit as Rankin did, in my view.
Well, that seems a good place to end on. Can I thank both Trevor and Fintan for their excellent presentation. A lot of effort went into putting it together, and I think it's come across certainly that Neville is a very important character, and I'm glad that he was a vice president of this institution. I'd say he would have been president, except he was probably too busy with his work. But certainly it's great to have somebody like Neville acknowledged. And incidentally, there is talk at the moment of reintroducing the transactions of the institution. I know a lot of people have felt that this was a bad day when we stopped having the transactions, because excellent presentations like this tend to just go into the ether or maybe into the cloud or something, and that's it. We don't hear anything more about them. So I would hope that the authors would, the presenters would accept an invitation that somehow or other the presentation tonight could be published in some form or other. And so on that note, I'd like to just invite you to give your usual appreciation to the authors.